This is the video for 9.6, which is solving exponential equations. This video will be a little bit longer than the rest of them just because it is going to involve several examples of solving exponential equations, and they can take a little bit of time. So we're going to start off with a couple of examples here, nothing too tricky to begin with. And we start off with 3 to the x is equal to 12. Now, you've got a couple of options here. You can rewrite this in logarithmic notation, and there's a way that you can get to writing it in logarithmic notation without necessarily doing a whole lot of work. And essentially, if you look at the equation, 3 to the x is equal to 12. I'm actually going to leave a little bit of space here. What we want to do is we want to get to this x, and remember that we said that the log function is what gets us to our exponent. So we can essentially take log base 3 of this, and this will get us to our logarithmic notation, which is x is equal to log base 3 of 12. Now, since this is log base 3, we would have to do the change of base formula to either log base 10 or the natural log of either of these, change of base formula, so that we can find a decimal approximation. This is the exact answer, log base 3 of 12. But if we want the decimal approximation, we would say, okay, the natural log of 12 divided by the natural log of 3. And so again, if we pull up our calculator here, all we have to do is type in the natural log of 12 and close parentheses divided by the natural log of 3 and close parentheses. And we end up with approximately 2.26. So that's one way you can go about doing it, is putting it into the logarithmic notation and then doing the change of base formula. There's another way that you can do this, and I'm going to kind of do this over to the side. The other thing that we can try to do is just apply the natural log to begin with. If we take the natural log of both sides, the natural log of 3x is equal to the natural log of 12, then our properties of logarithms tell us that that exponent is going to come down as a coefficient. So we're left with x times the natural log of 3 is equal to the natural log of 12. And now all we have to do to solve for x is divide by the natural log of 3. And you can see how this gets you to the same answer, that x is equal to the natural log of 12 divided by the natural log of 3. And this is the same thing that we got with our other method. So I want you to pause the video here and try example 50. So if you worked through this example, you should have found that x was equal to approximately negative 5.94. And if you wanted to check this, it's very easy. All you have to do is plug this in and say, okay, what is 4 to the negative 0.594? So if you plug that into your calculator, and again, this is going to be an approximation, you would get 4, hit that caret button to get your exponent, negative 0.594. And we get 0.439 if you round up. So this does work out. So we just went through and found the exponent that we need to raise 4 to get the decimal 0.439. It's not always just a single exponent. Sometimes we either have a coefficient on an exponent, like we do in this next example, or we have a coefficient and a sum, which we do in the following example. We just go through the same process. You're going to take the natural log of both sides, so you end up with a natural log of 3 to the 2x is equal to the natural log of 0.21, and then we bring that 2x down as your coefficient, so we get 2x times the natural log of 3 is equal to the natural log of 0.21. And then you notice if you want to solve for x here, you need to divide by 2 natural log of 3. You need to get rid of both of those terms. So we'll do that on this side as well. And so we end up with x being the natural log of 0.21 divided by 2 times the natural log of 3. And we have to be very careful when inputting this into our calculator because we need to make sure that we have this entire denominator in the calculator. So we would take the natural log of 0.21, close that parentheses, divided by, and now we need parentheses for the denominator because we need to make sure that we include the 2 times the natural log. If we don't put those parentheses there, the calculator won't recognize that both are in the denominator. So then we close all of our parentheses and we end up with negative 0.71. And again, if you wanted to check, then you would just simply plug this in. You would say 3 raised to the 2 times the negative 0.71. And you'd come over here to your calculator and you'd say, okay, 3 raised to the, and we've got parentheses, 2 times negative 0.71, and close that parentheses. And we end up with 0.21, so we're good. So we can check. So this next example is a good example of what happens when you've got two different bases. So picking the log of one or the other is not really going to help you much with bringing down the exponent from the other term. So this is where the natural log process really does help. So if we take the natural log of both sides, so the natural log of 2 to the 2x plus 1 is equal to the natural log of 5x. Again, bring those exponents down, and we want to make sure that we put this 2x plus 1 in parentheses because it's coming down as one whole factor. So we've got the natural log of 2 left is equal to x times the natural log of 5. Now you may be saying, okay, what do I do next? I've got an x on the left side and the right side. Well, what you need to do here is you need to distribute, and this is why those parentheses are so important. So we're going to end up with 2x natural log of 2 plus natural log of 2 when you distribute to the 1 is equal to x natural log of 5. Now I'm going to move everything with an x term to the right side, so I'm going to subtract off this 2x natural log of 2 from both sides. Now you might be inclined to try to combine these in some way, and you can, but be very careful about how you do. So if we come up here to the next side, we end up with the natural log of 2 on the left side, and I'm just going to write this out the first time as x natural log of 5 minus 2x natural log of 2. Now essentially what we need to do is we need to factor out the x. So we're going to factor out this x and this x, and we're going to be left with the natural log of 5 minus 2 times the natural log of 2. So we've just got the remaining pieces. We pulled out the x, left the natural log of 5 minus 2 and the natural log of 2. So in this case, to solve for x, our last step is simply to divide by that entire term. Again, the parentheses are very important because we're dividing by the entire term. We can't split that up anymore. And we're going to do the same thing and divide over here. So finally, we are left with x is equal to the natural log of 2 over the natural log of 5 minus 2 times the natural log of 2. Now we can simplify this a bit before we plug it in the calculator if we use our properties of exponents on the denominator. Remember that this 2 out front can come up as an exponent, so you're left with the natural log of 5 minus the natural log of 2 squared, which is 4. And then remember that subtraction outside becomes division inside. So this can be the natural log of 2 divided by the natural log of, and only the denominator can get combined to be 5/4. Again, the 4 is coming from the fact that you had 2 squared. And now, if you wanted to plug it in the calculator to find an approximation, we could do so. And it's a little bit easier. Or you can plug it in as the complicated mess we had before. So we've got the natural log of 2 divided by the natural log of 5/4. And we get approximately 3.11. If you wanted to check to make sure that worked with the first way we had this, you'd have to be very careful with parentheses. You would take the natural log of 2 divided by parentheses the natural log of 5, close parentheses, minus 2 times the natural log of 2, close parentheses, close parentheses. And again, you end up with that 3.11. I want you to pause the video at this point and see if you can try example 53. So for this example, you could have still used the natural log. I chose instead to use log base 10, the common logarithm, because it's a base 10. We've got the anti-logarithm there. And so that's automatically, log of 10 is automatically going to give us our exponent negative x. And so then we take the log of the other side, 0.146. So then all we have to do is multiply both sides by -1, and then we can plug it in our calculator, and you end up with approximately 0.836. Now if you use natural log in this case, that's fine. You should have still ended up with x being 0.836. On this next example, it's really beneficial to use the natural log because we've got e. So again, I want you to pause the video and work through this example. So for this example, like I said, it's very opportune to use the natural log because the natural log and e are inverse operations, so you're left with the exponent 2x. On the right side, you're left with the natural log of 40.5, so all you have to do is divide by that coefficient of 2. Now you have to be very careful when putting this in the calculator that you close the parentheses after the 40.2. That's the only thing you're taking the natural log of. If you forget to close that parentheses, then you're dividing the 40.5 by 2 instead of the natural log of 40.5. So you want to make sure you're very careful with order of operations and parentheses when plugging things into your calculator. Okay, we're going to do a few more examples here. This next example, we can use the natural log in this case. So we would have the natural log of 9 is equal to the natural log of 15 times 1 plus e to the negative x. Now we can use our properties of logarithms. This is why we went over them. We've got the natural log of 9 is equal to, well, this is multiplication here, and we've got an exponent here. So we end up with the natural log of 15, and we can bring that exponent down as well. So this actually ends up being a minus x times the natural log of 1 plus e, and 1 plus e is just a number. We can't distribute the natural log, but we can just remember that it is just a number. So now when we are trying to solve for x, we want to move this natural log of 15 over, so we will subtract it because we've got addition and subtraction going on. And so we have the natural log of 9 minus the natural log of 15. Again, I don't want to see anybody trying to subtract within these natural logs because they are separate numbers. Remember that subtraction means division inside. So if you're going to combine them, you have to use the properties of logarithms properly. On the other side, we're left with x times the natural log of 1 plus e. And so again, the only thing we have to do here is divide by that negative and divide by the natural log of 1 plus e. So when all is said and done, x is equal to, we can use our properties of logarithms to rewrite this as the natural log of 9/15, and you can reduce that fraction, divided by negative natural log of 1 plus e. Okay, so if we plug this into the calculator, we end up with the natural log of, and we can end up either putting in 9/15 or 3/5, and then we are dividing that by negative natural log of 1 plus e. And remember, the e is right here above your division symbol. So we close that parentheses, and we're left with approximately 0.389. Another example, this is similar to the last one, except the exponent is only on that single term instead of on the parentheses. So in this case, we can do a little bit of algebra before. We can divide both sides by our coefficient 425. And 150 divided by 425, if you reduce that fraction, is 6/17. So we have 6/17. So if you reduce that fraction, you end up with 6/17 is equal to 1 minus e to the x over 5. We can do some algebra here and subtract that 1 over. So we have 6/17 minus 1 would be negative 11/17 is equal to negative e to the x over 5. Multiply both of those sides by negative 1 and both become positive. And then we want to take the natural log of both sides. So we're left with the natural log of 11/17 is equal to the natural log of e to the x over 5. Again, remember that natural log of e just gives us our exponent. So this is just x over 5. So now all we have to do to solve is multiply both sides by 5. So x is equal to 5 times the natural log of 11/17. So again, if we plug that into our calculator, we have 5 times the natural log of 11 divided by 17. So we have negative 2.18. And that's our answer. We have a few more examples here and then an application. Our first example here has e to the 2x minus 7e to the x is equal to negative 12. Now, you might be tempted to try to combine the e's, but in this case they have different exponents, so we can't combine them. You can, however, think about this as being a quadratic equation. And if you let e to the x be some other variable, say a, then technically, if you think about e to the 2x, well, this is really e to the x squared, right? Because you would have 2 times x to get your exponent, so this would be e to the x squared. So this would be a squared minus 7a is equal to negative 12. Now we can use the quadratic methods that we learned before to solve this equation. So we would have a squared minus 7a, and we add the 12 over, so we would have plus 12 is equal to 0. And then we would ask ourselves, what two factors of 12 are going to add to give us negative 7? Well, we're going to end up with a minus 3 and a minus 4. So in this case, we end up with a being equal to 3, and in this case, we end up with a being equal to 4. Now, if we plug e to the x back in, if e to the x is equal to 3, I'm going to leave a little bit of space here for the 3. Then we can take the natural log of both sides. The natural log of e is just going to leave us with the exponent x. And we are left with a natural log of 3. You can leave it as that, or you can find the approximate. And the approximate here, the natural log of 3, is just 1.1, approximately. I want you to pause the video here and find what x is equal to when a equals 4. So in this case, you should have ended up with x being equal to 1.39, or approximately. So we end up with 2 answers here, and we could go back to check to make sure that they both work, and they do. And so in this case, we end up with the 2 answers, either the natural log of 3 and the natural log of 4, or if you want the decimal approximation, 1.1 and 1.39. We have one last example before we get to the application, and this example seems like it should be relatively straightforward, and it is. There's 2 different approaches you can have to this. The one thing to be careful of, though, is the fact that, yes, you have the same base here, so you've got 2 and 2, but one has an exponent and one technically has an exponent that is understood to be 1. So there's 2 different ways that you can go about this. One is you can divide both sides by the 2. Another way you can do it, and this only works when you have the same base, is you can add those exponents. So we'll do it both ways. First time, let's go through and just divide by 2. Then we would be left with 2 to the 3x minus 1 is equal to 8. Again, we want to apply the operation, the function natural log to both sides so that we can bring down that exponent, and we want to put it in parentheses. So we have 3x minus 1 times the natural log of 2 is equal to the natural log of 8. And then we can divide by the natural log of 2, and that would leave us with 3x minus 1 is equal to the natural log of 8 divided by the natural log of 2. And then we would have to add 1 to both sides. So we would have 3x is equal to the natural log of 8 divided by the natural log of 2, and then you would add 1. And finally, you would divide both sides by 3. And to write this cleanly, we can distribute this 3 to each part of the top. So this would be the natural log of 8 over 3 times the natural log of 2 plus 1 over 3. So we've divided both of those there. Again, if you wanted to find the decimal approximation, you could. You would have the natural log of 8, close the parentheses, divided by parentheses 3 times the natural log of 2, close parentheses, plus 1/3. And you're left with 1.333. Technically, if you look at this to simplify, this would be the natural log of 8. If you bring this exponent up, this is the natural log of 2 cubed. 2 cubed is 8. So technically, this entire thing is 1. So you end up with 1 1/3. So let's look at how we would do this the other way. So if you think about multiplying bases, we would add the exponents. So we would have 1 plus 3x minus 1, which is just simply 3x. So in this case, we end up with 2 to the 3x is equal to 16. Again, we're going to take the natural log of both sides, and we're going to be left with 3x times the natural log of 2 is equal to the natural log of 16. Now to solve for x, we divide by everything else, which is 3 natural log of 2. And we are left with x is equal to the natural log of 16 divided by 3 natural log of 2. If we wanted to compare to make sure this was the same thing, we can go to our calculator, and we take the natural log of 16 divided by parentheses 3 natural log of 2, which again we said was the natural log of 8. And we end up with that 1.33, so we end up with 1 1/3 again. So take a second, make sure you're comfortable with the methods of solving exponential equations, and then our last example is an application. So a common example of the exponential function and exponential decay is blood alcohol concentration, the amount of alcohol present in a person's bloodstream. So relative risk is defined as the likelihood of one event occurring divided by the likelihood that a second event will occur. And it's been found that the relative risk R of causing an accident while intoxicated can be modeled by the following equation, e to the kx, where k is a constant and x is the blood alcohol content. So research indicates that the relative risk of a person causing an accident with a blood alcohol content of 0.02% is 1.4. So they've done that relative risk for us and found the ratio 1.4. We want to find the constant k. So we can plug this into our equation. We have 1.4 is the relative risk is equal to e to the k is what we're looking for, and then we said x is 0.02%. So remember, as a decimal, we've got to move that decimal 2 more places over. So this is 0.0002 as a decimal. Now to solve this, we simply take the natural log of both sides. So we end up with the natural log of 1.4, the natural log of e to the k times 0.0002 is just 0.0002k. And now To find K on its own, we just divide by that decimal point 0.002. So K is equal to the natural log of 1.4 divided by 0.0002. So if we come over here to our calculator to find a decimal approximation for K, we have the natural log of 1.4 divided by 0.0002. And we end up with 1682.36. So it's a rather large constant, but keep in mind that those blood alcohol concentration was rather small. So let's take a look at some relative risks. We want to find the relative risk, and again, remember the relative risk is the likelihood of one event occurring divided by the likelihood that a second event will occur. So the relative risk for causing a car accident, depending on if you are intoxicated, it's 1.4 chance that you will have an accident if you have a 0.02% blood alcohol content. Let's find the relative risk of a person with a blood alcohol content of 0.17, which is really high. So in this case, we now found our equation. If we want to, we could just rewrite the equation here. R is equal to e to the 1682.36x. So that is our equation. We are going to plug it in, e to the 1682.36, and our x in this case, again, move that decimal place over, 0.0017. And we can just plug it straight into the calculator as we see it. We have e to the x we want to use because we have that exponent, 1682.36 times 0.0017. Close the parentheses. 17.5 essentially. So what this is saying is that your likelihood of getting in a car accident is 17.5 times higher if you have a 0.17 blood alcohol content than if you were just driving normally. So the next question asks which blood alcohol content corresponds to a relative risk of 100. So we want to know the likelihood that it would be 100 times more risky to drive with what blood alcohol content. So in this case, our R is 100, and we're plugging it into our equation. E to the 1682.36, that's our K, and then we have X. We want to find X. So again, we're going to use the natural log to get rid of the E. So we're left with the natural log of 100 is equal to 1682.36x. So all we have to do is divide by that coefficient. So x is equal to the natural log of 100 divided by 1682.36. So again, if we go to our calculator, we've got the natural log of 100, make sure to close that parentheses, divided by 1682.36, and we get 0.0027. So again, if we wanted to convert this back to percentage, this would be a 0.27% blood alcohol content. So I want you to try the final example here. Ohio law prohibits anyone driving with a relative risk of 4 or higher. At what blood alcohol content should a driver be arrested and charged with a DUI in Ohio? So for this example, you should have found that x was equal to 0.00082, and that corresponds to 0.08%, which is the legal cutoff limit for DUI in the state of Ohio. So please go online now and complete your homework for this section, and then watch the final video for Chapter 9.